Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad HAKIM bin AHMAD KHAIRUDDIN, metric number 281514. First of all, the introduction of ordinary differential equation. A differential equation is an equation that includes a function and one or more of its derivatives. In most practical problems, a function is a physical quantity, the derivative corresponds to the rate of change of this quantity, and the equations determine the relationship between them. The ordinary differential equation has a remarkable ability to predict the world around us. We can use the first order ordinary equation to solve the exact flow of the water level. There are four ways to solve first order differential equations, which are linear equations, separable equations, exact equations, and Bernoulli differential equations. Next is the background of this application. Many civil and environmental engineering systems employ water tanks. Networks for distributing water, facilities for treating water, and desalination plants are a few examples of these systems. One of the crucial tasks usually carried out during regular maintenance and emergency operations are draining a tank. But in this video, we are going to discuss the application of estimating the time needed to drain a container of apple cider. This application uses a first order differential equation.
Assalamualaikum and hi, my name is AFIQAH ADILAH BINTI SAHAK, metric number 281559. Now I will present the methodology part. The purpose of this study was to demonstrate an understanding of ODE to relate to real-life application. This study used the second data from the internet by Zamera Webb, who had run a calculation and experiment about draining of water from a container. In this project, we will use ODE to solve the problem of drainage of water from a container. Then, we were able to predict the time it would take for water to flow in the container by experimenting with available material. In this study, the ODE that we use are linear equation and separable differential equation. The form of linear equation is y prime plus pty equal gt. We give an in-depth overview of the process used to solve this type of differential equation, as well as a derivation of the formula needed for the integrating factor used in the solution process. Below show the problem-solving strategy for separable differential equation. First, check for any value of y that make gy equal 0. Rewrite the differential equation in form dy gy equal fx dx. Integrate both sides of the equation, solving the resulting equation for y if possible. And lastly, if an initial condition exists, substitute the appropriate value for x and y into the equation and solve for the constant. That's all for me. Thank you.
My name is YONG with metric number 279598. Now, I'm going to explain the model derivation of the tank draining experiment. First, we know that the rate of accumulation of volume is equal to the rate of change in height multiplied by the cross-sectional area. So our first balance equation now is this. Then the principle of conservation energy leads us to the Bernoulli equation. Next, let's take a look on the model of our experiment. Bernoulli equation is applied to these 2 points. Since P1 and P2 are almost at the same pressure, so they can be crossed off together, the density of water also can be cancelled from all these remaining terms, and it does not change at all. Rearranging gives the following equation. Further simplification is possible if we neglect V2 squared. This is defensible because V2 is much larger than V1. We also can replace the difference in heights between 2 points with h. This can be written as the following equation. Having solved the velocity at point 2, which is the velocity out in the simplified balance equation above, we can now put everything together. Since area, acceleration, and g are all constant in our model, we can lump up all the constants together and as k and write the following equation. We have derived the differential equation for the height of fluid in the tank by using principle of physics and some appropriate simplification. Separation and integration lead us to a solution of water height as a function of time. Here, we specify the constant of integration in terms of the initial height at t equal to 0. Rearrangement gives the solution of our differential equation. When h equal to 0, we can determine the time necessary for the tank to drain. If we substitute for the constant k, we can find the equation to calculate the final time is the equation as shown below. That's all from me. Thank you.
My name is Mable Xuewei, my metric number is 279652. Now I'll bring into the background of the experiment. Let us take a look into the container of the apple cider. It is given that the initial height of the water flow is 14.6 cm, the diameter of the hole is 0.65 cm, and the area is 4.08 times 10 to the negative 5 meters squared. And the diameter of the whole container is 11.8 cm, and the area is 10.22 times 10 to the negative 3 meters squared. And remember that the gravity is always 9.81 meter per second square. Let us look at the experiment model. There are two questions we have to solve. The first one is what is the lump constant of the container, and what is the predicted draining. To solve the lump constant, we just have to take the formula we proved just now, substitute all the values given, and find that the value of K is 0.01768. Next, to solve the predicted value draining time. With the same method, substitute values into the formula proved earlier, and we can get the draining time to be estimated as 432 seconds. To conclude, the ordinary differential equations can be used to solve applications that happen in daily life. The exit flow of the water level can use the first ordinary equations to solve. We can see that this differential equation is related closely to the gravity because the water is flowing downwards towards the ground. From this application, we can know that the total time of water flowing out of any container with the ordinary differential equation proved by the Bernoulli's equation. In this application, we can find that the time of flowing water from the apple-sided container is 432 seconds, which is estimated to be 7 minutes. Thus, no matter what size the container is, we can still predict the time to empty the full container. So that is all from our group.